On April 9th, 2026, Avihu Mordechai Levy at StarkWare posted a construction called Quantum Safe Bitcoin, or QSB. Here's what it does. Once legacy coins are already locked inside a QSB output, QSB lets the owner spend them safely, even against a quantum computer. It fits inside today's Bitcoin script. No soft fork required. The catch, as we will see, is that moving coins into a QSB output in the first place is a separate problem. The headline's called QSB a rescue package. The paper itself is more careful. Today we walk through what the construction does, who invented the clever trick behind it, the honest numbers, and the 5 things it still cannot fix. We have a companion video on Google Quantum AI's April 2026 resource estimate for breaking Bitcoin's elliptic curve signatures. Link in the description. That video was about the threat. This one is about the escape hatch. Taken together, they describe the 3-piece shape of Bitcoin's post-quantum story: a sharper threat model, a clever last resort escape for legacy coins, and a still unfinished protocol-level mitigation path. QSB in one sentence. It is a new Bitcoin locking script that lets you spend legacy outputs safely, even under a quantum adversary, using only hash-to-signature puzzles that Bitcoin script already accepts today. No soft fork, no new opcodes, no new BIP required. The whole thing fits inside the consensus rules Bitcoin already runs. That is the clever part. What it costs to get there and what it leaves unsolved is the rest of the video. Before the numbers, the mechanics. QSB did not appear from nowhere. It is a targeted fix to an earlier construction that almost worked. Let's start with the construction QSB builds on. Robin Linus's Binohash, published in 2026, is a transaction introspection digest construction for BitVM-like use cases. It runs using only opcodes Bitcoin script already supports today, with no soft fork additions. Its security under quantum attack rested on a proof-of-work puzzle over ECDSA signature sizes, which in turn rested on a minimal R assumption. You could not find a curve point whose R coordinate was smaller than the known minimum. Classically, that search is about 2 to the 96th work, which is safe. Under Shor's algorithm, you can compute the discrete log of a smaller R value directly, and the puzzle falls apart. Levy calls it a total break. QSB reuses Binohash's mechanical frame and swaps that one broken puzzle out. QSB's move is surgical. It keeps the Binohash frame, then swaps out the one-component Shor breaks. The signature-size puzzle goes away. In its place, a hash-to-signature puzzle whose security rests only on RipMD 160 pre-image resistance. Hashes do not fall to Shor. The quantum adversary loses the advantage that killed Binohash. Same script budget, different puzzle, different quantum posture. The core claim of QSB rests on one clean fact. RipMD 160 pre-image resistance is not touched by Shor's algorithm. Shor attacks structured problems like discrete logs and factoring. It does not speed up hash inversion. So the second pre-image resistance of QSB's recommended configuration A, at about 2 to the 118th operations under Shor, is simply the same number a classical attacker faces. That is the whole point. The whole construction has to fit inside Bitcoin's existing script rules. 201 non-push opcodes. Under 10,000 bytes per script. QSB configuration A lands exactly on 201 opcodes and well under the byte budget. Bitcoin's consensus already accepts this today, with no soft fork, no new BIP, no new opcodes. That is what makes QSB deployable, without coordination, at least in principle. There is an important caveat to the no soft fork framing. QSB only works as a legacy bare script construction. SegWit and Taproot cannot host it directly. Any coins you want QSB protected have to be moved into a QSB output through a normal Bitcoin spend first, and that migration spend is itself a classical quantum unsafe transaction. Once a quantum attacker exists, the migration window is the window they can win. QSB protects coins already inside the box. Getting them inside is a separate problem. Before we get to the numbers, one piece of credit that the coverage mostly skipped. The core observation behind QSB is not Levy's. The paper is careful about this, and the story should be too. The hash-to-signature observation at the heart of QSB belongs to Robin Linus. He published it in the SHA-2 ECDSA repository, and the QSB paper cites that work as reference 8. Levy assembled the full Bitcoin-facing construction around it, which is genuine engineering work. But the clever primitive, the one sentence that makes the whole thing possible, is Linus's. That credit matters because most press coverage collapsed it to a StarkWare announcement. Start with the observation QSB rests on. Hash outputs can, with some probability, parse as valid DER-encoded ECDSA signatures. DER, short for Distinguished Encoding Rules, is the strict serialization format Bitcoin uses for signatures. Why does that matter? DER has rigid format rules, but Bitcoin's strict encoding check is relay policy, not consensus. So the trailing SIG hash byte is left unconstrained at the consensus level. That unconstrained byte is the slack that lets a random 20-byte RIPMD 160 output accidentally parse as valid. Now the probability. Levy works it out as roughly 1 in 2 to the 46th for RIPMD 160, with a matching figure of 2 to the negative 45.4 for Shor, 256. Grind inputs until a hash output lands on a valid signature, about 2 to the 46th hash evaluations per hit. That is the whole puzzle. Security rests on pre-image resistance, nothing else. QSB script construction wires that observation into Bitcoin in 3 moves. First, a hard-coded signature nonce with a fixed SIG hash, all byte lives in the locking script. Second, the spender recovers a key nonce using the SIG hash of the actual spending transaction, which binds the puzzle to that specific transaction. Third, the script checks whether the RIPMD 160 hash of that recovered nonce is itself a valid DER signature, verified against a second recovered key via checksig verify. Transaction pinning costs 5 opcodes here, down from Binohash's 13. The whole thing is tighter. With the mechanics in place, what does the recommended configuration actually buy you? This is where QSB either earns its keep or doesn't. Configuration A is the one Levy recommends. It lands on exactly 201 opcodes, right at the script limit, well under the 10,000 byte cap. Digest size of 80.4 bits. Second preimage resistance of about 2 to the 118th under Shor. Collision resistance of about 2 to the 78th under Shor, and roughly 1 grinding attempt per transaction, which is what makes the off-chain compute cost bounded per spend. Here is the central result. At configuration A's parameters, Shor's algorithm offers 0 advantage against QSB. An attacker with a full fault-tolerant quantum computer faces the same 2 to the 118th second preimage search a classical attacker does. Hashes do not factor. They do not have hidden periods, they just resist preimage attacks, and Shor does not help you find preimages faster. That is the whole point of the construction. Grover is the interesting column. Staying on configuration A, second preimage resistance drops from about 2 to the 118th under Shor, where Grover offers no help, to about 2 to the 59th under Grover's quadratic speedup. That sounds bad until you look at the realities. Grover is hard to parallelize. Running it on K machines gives you a square root of K speedup, not K. And Grover against a 2 to the 46th RIPMD 160 puzzle target requires implementing SIG hash evaluation and ECDSA, key recovery, as reversible quantum circuits. That is much further out than Shor against the elliptic curve. The off-chain cost per spend breaks down roughly as $25 to $50 for transaction pinning, $25 to $50 for round 1, and $25 to $50 for round 2 on commodity cloud GPUs at current spot pricing. That is a total of about $75 to $150 per spend. The paper widens that to $75 to $200 to account for implementation uncertainty, and the abstract rounds it to a few $100s. Two things matter. First, that is roughly 9 times the equivalent Binohash work. Second, and more importantly, this is not the Bitcoin transaction fee. It is the off-chain GPU compute the spender buys before broadcasting. Any coverage that collapses it to $200 per transaction is wrong. Levy is unusually direct about what QSB cannot do. Section 1.3 of the paper reads, like a limitations list, you would normally have to extract yourself. 5 entries. All 5 matter. The big one first. Taproot is worse, not helped. Footnote 1 of the paper is blunt. Under Taproot, the situation is strictly worse. Every Taproot output is spendable via the key path, meaning knowledge of the private key corresponding to the internal public key suffices to spend it, regardless of the script conditions in the tap tree. So every P2TR-UTXO remains a standing target under Shor. That is the same Taproot exposure point the Google paper flagged, and QSB does nothing to fix it. Next, non-standard relay. Section 3.5 of the paper describes a script that exceeds default relay policy limits. A regular Bitcoin node will not propagate it. The spend path depends on finding a miner or a private mempool service willing to relay non-standard transactions. Levy names Marathon Slipstream as one practical example today, and it is the clearest one. But the framing is example, not sole option. Depending on any specific private mempool service is not a resilient broadcast path on its own. Then the ongoing cost. Off-chain compute per spend. Each QSB spend costs roughly $75 to $150 of GPU time before you ever pay a Bitcoin transaction fee. And that work is per transaction, not amortizable across a wallet. Spending 10 outputs to 10 destinations means 10 separate rounds of off-chain grinding. It makes small value spends nonsensical and concentrates the cost on high-value recoveries. Fourth, does not scale. Quoting section 1.3 directly, the off-chain computational cost and the on-chain transaction cost do not scale to the full range of users, amounts, and throughput that Bitcoin targets. This is an evacuation route, not a commuter lane. An exchange with a post-quantum rescue plan can imagine sweeping cold storage this way. Bitcoin as an everyday payment network cannot run on QSB. Last, no Lightning. From the same section, QSB does not yet cover all Bitcoin use cases. For example, Lightning network channels, payment channels, multi-party protocols, and anything depending on pre-signed off-chain state are out of scope. Levy's own framing in section 1.3 is that QSB should be treated as a last resort measure. That is the author of the paper saying it, not a skeptic. So, does QSB change the migration requirement? A custodian reading this paper and asking if they can skip post-quantum migration now should walk away with the direct answer. No. QSB is prophylactic, not treatment. It protects coins already sitting inside a QSB-locked legacy bear script output. Moving coins into that output is itself a classical, mempool-exposed Bitcoin transaction. A fast enough quantum attacker can race it or replace it. If such an attacker exists, when you try to migrate in, the migration transaction is the window they win. The paper closes its own limitations section with this. It remains necessary to continue the ongoing effort to research and implement the best possible solution for Bitcoin, one that is maximally efficient, user-friendly, and answers Bitcoin's needs through protocol-level changes. Protocol-level changes are still necessary. BIP 360 is one prominent draft path. It proposes a pay-to-Merkle root output type that removes Taproot's quantum-vulnerable key path. BIP 360 is a structural mitigation, not itself a post-quantum signature scheme. Future post-quantum signatures or opcodes are a separate later step. QSB does not replace any of that. It buys time around the protocol work at a cost for a specific class of holders. Put together, the three papers describe the shape of Bitcoin's post-quantum story as of April 2026. The Google paper sharpened the threat, tightening the resource estimate for breaking ECDSA on SecP. QSB gives legacy holders a narrow, expensive last resort escape hatch inside today's Bitcoin script. BIP 360p2MR is still a draft soft fork proposal. It primarily addresses the long exposure side, removing Taproot's quantum vulnerable key path. Short exposure protection during the broadcast to confirmation window may still require future post-quantum signature support. Threat, escape hatch, mitigation. 3 pieces. All 3 matter. None of them stand alone. 3 takeaways. First, QSB exists and works in principle, inside Bitcoin's existing script rules, with no soft fork. The construction is well specified, the paper's core idea is coherent, and the no soft fork claim holds. Second, it is expensive and non-standard. $75 to $150 of off-chain compute per spend. Transactions are consensus valid but non-standard, so they reach a miner only through private mempool paths like Slipstream. No help for Taproot, no Lightning, does not scale. Third, protocol-level work is still necessary. QSB buys time around BIP 360 and future post-quantum signature support. It does not replace them. Threat, escape hatch, mitigation. The escape hatch is real. The protocol-level work is still the job. I hope this was useful. Hit like and subscribe for more on post-quantum cryptography and zero-knowledge proofs.